In this video, we are going to continue learning about limits, and we're going to focus on how to compute limits algebraically. We're going to work through a couple methods. The first method we always want to try is, can I directly substitute to evaluate that limit? Now, what direct substitution means is, can I take the number that x is approaching, or that our variable is approaching, directly sub it in place of all those x's or in place of our variable, and get a numerical answer out. If that works, then we want to go ahead and use direct substitution. Now, not all limits will work that way, which is why we're going to have a couple other methods that we will talk about that will involve some algebraic manipulation. So one could be factoring. We'll be talking about how to multiply by the conjugate, maybe how to find a common denominator, and then the special case where sometimes we have to deal with an absolute value and really think about the piecewise definition of an absolute value. So in this video, we are going to focus on the 5 concepts on the left side of this list, and later on we'll talk about a couple other techniques we have for computing limits. So let's look at example 10. In prior videos, we have talked about the importance of understanding the limit notation and how to read and pronounce the question. So why don't you guys pause the video and go ahead and read this statement that question 10 is asking out loud to yourselves. So in question 10, this says the limit as x approaches 3 of x squared times 2 minus x. And again, I'm going to keep stressing the importance of understanding what the question is asking and also understanding the notation behind it. So we haven't taken the limit yet. This is the problem. They're asking us to take the limit as x approaches 3 of x squared times 2 minus x. So the first method we want to try is direct substitution. I'm going to kind of keep a list going on the left-hand side depending on how many methods we might need to try to be able to get an answer. What direct substitution would mean is that anywhere I have an x, I'm going to substitute in 3 since x is approaching that value of 3 in this problem. When I do that, I'll get 3 squared times 2 minus 3. Another thing to note is I don't have the word limit in front of here anymore. And the reason I'm not writing the limit as x approaches 3 in front of this is because I've evaluated this limit already by doing this direct substitution and substituting in 3 in place of all the x's. Simplifying this down, we can use order of operations and we get 9 times negative 1, which will give us an answer of negative 9. And since negative 9 is a valid numerical answer, direct substitution did work in this case, and we can directly substitute in 3, and we get out that the limit for this function is going to be equal to negative 9. Let's look at example 11. Why don't you guys pause the video and read this statement out loud to yourself first, and then we'll check that together. So in example 11, it says the limit as x approaches 2 of x squared plus 2x plus 4, all divided by x plus 1. What do you guys think? Do you think direct substitution will work in this case? So let's find out. If I directly substitute in, I'm subbing in 2 now in place of all the x's. So I'll get 2 squared plus 2 times 2 plus 4, all divided by 2 plus 1. Again, I don't have the limit as x approaches 2 written in front of this because I've already taken the limit by doing direct substitution. And once we've evaluated the limit, we no longer have that notation in front. So let's simplify this down and see if I get a numerical answer. In the numerator, we're getting 4 plus 4 plus 4, all divided by 3. So we end up with 12 over 3, which will give us 4 as our final answer. Since 4 is a valid numerical answer that we can get out, then direct substitution did work on example 11 as well. Let's look at example 12. Why don't you guys pause the video and read the statement out loud to yourselves, what the question is asking, and then compute the limit and see if direct substitution works in this case or not. So what do you guys think? Did direct substitution work in this case? Let's find out. So if I directly sub in, this problem is saying the limit as x approaches 1 of x squared minus 1 over x plus 1. To do direct substitution, I'm going to substitute in 1 in place of all the x's. So I'll get 1 squared minus 1 over 1 plus 1. Again, I do not write the limit in front since I've substituted that in already. This will be equal to 0 in the numerator, since 1 squared is 1. 1 minus 1 gives us 0, and then I have 2 in the denominator. Well, what happens when I get 0 over a non-zero number? Well, this will end up being equal to 0. So it's okay to have 0 in the numerator as long as I have a non-zero number in the denominator, and that will always reduce down to be 0. So in this case, direct substitution worked again. Oops. Let's make that clear so we can read it. So direct substitution did work again in this case, since I ended up getting a valid numerical answer out. Now I want to kind of bring to your attention that whole divide by 0 concept. And it's something that I get questions about all the time in really any class, any math class that I end up teaching. And in my wall, in my classroom, I have a sign. It says divide by 0, and then it has the okay, and then it has the no sign. Well, the okay is this case that we're looking at. So okay is when I have 0 in the numerator and a non-zero number in the denominator. That's okay. That will be equal to 0, and that will end up working out, hence the phrase okay. Now on the flip side, I have the sign that says no, where I have a non-zero number in the numerator divided by 0 in the denominator. In this case, this is a no, and I end up getting an undefined answer. Sorry, I can't fit the word undefined there, but UND is standing for undefined. And the reason that that's happening is I'm dividing through by 0, and in math we don't get a valid answer when that happens. These are the cases that we're looking for where maybe we have to do something else in terms of limits. One of those cases could be if I had this no case, where I had a non-zero number over 0. We'd have to think through that limit a little bit more. The other case that we're going to see start happening is this 0 divided by 0 case. So 0 divided by 0 is what we call an indeterminate form in mathematics. And in terms of limits, what that's going to mean is that I'm going to have to do a little bit more work, maybe some algebraic manipulation, to figure out what that limit would be. So as we go through the next couple examples, we might be seeing some of these cases where we get 0 over 0, and that doesn't mean that the limit doesn't exist. It just means that that limit, that form, is indeterminate, and I have to be strategic as I manipulate through the problem and think about how else I could solve that limit. So let's look at a couple more examples. So in 13, it says the limit as x approaches -1 of x squared minus 1 over x plus 1. Well, let's continue doing what we've done. Let's try a direct substitution. Why don't you guys pause the video and try directly substituting in for this limit, and let's see what happens. So if we directly substitute in, we get -1 squared minus 1 over -1 plus 1. Again, I wouldn't have the limit since I've already taken it by doing the direct substitution. Now when I simplify this, in the numerator, -1 squared gives me +1, so I get 1 minus 1 over 0, since -1 plus 1 will give me 0, and I end up with the 0 over 0 issue. This is an indeterminate form, and what that means is that I need to be a little bit more strategic with how I take this limit, and what it also tells me is that unfortunately, direct substitution is not going to work. Instead, I need to algebraically manipulate this limit. Get that down there. So we have to think about different ways that we can algebraically manipulate this limit so that I don't get the indeterminate form and instead I get something that is valid. I'm going to scroll back up and let's look at this list. So this list up here of dealing with factoring, maybe finding the conjugate or a common denominator, those are going to be the three main types of algebraic manipulation that we're going to focus on in this video. So in example 13, what do you guys think? Could I factor maybe the original problem that I'm given? What do you guys think? So in this case, I could factor it. So everything I did up here with the direct substitution is helpful because I now know that I can't do a direct substitution limit. I have to try a different method. And because I got this 0 over 0 case, I know that it should be something that I can algebraically manipulate. So I'm not going to cross it off. It is part of my thought process as I'm thinking through these, but instead I'm going to continue this problem down below. Since I'm not going to directly substitute in, I need to still make sure that I'm writing the limit as x approaches -1 until I actually take that limit. And in this first step, what I'm going to do instead is factor it. So x squared minus 1 can be factored. It's a different set of squares, so it's x plus 1 times x minus 1, and then our denominator is already in factored form since it is linear. Now that this is factored, I can go ahead and cancel any common factors. Well, I have an x plus 1 in the numerator and an x plus 1 in the denominator, so those can go ahead and cancel out, and we're left with the limit as x approaches negative 1 of x minus 1, technically, over 1. Or, it's kind of silly to write over 1, we could just write x minus 1. One thing I want to point out is I have not taken the limit yet. I have not substituted in negative 1 in place of that x yet at all. And right now what we're doing is this kind of algebraic manipulation step with what's inside of our limit, which means I still need to have this limit as x approaches negative 1 in front of both of these statements. And if I forgot to write, I'm going to go ahead and highlight these, if I forgot to write these, then I would actually be losing points because my notation would not be correct, and I'd be saying that something is equal when it is in fact not equal. Now that I've algebraically manipulated it, I've kind of gotten rid of that issue of having 0 in the denominator. If I go ahead and do a direct substitution now, and I substitute a negative 1 for x, I'll get negative 1 minus 1. Notice that because I did that direct substitution step now, I do not write the limit any longer, and I can go ahead and simplify that and get negative 2. So this example we've seen where we did have to algebraically manipulate it first, and really this limit comes down to factoring and how can I kind of cancel out the issue, which was that x plus 1 in the denominator since it was making me divide through by 0. And the way we went through on canceling it was that we first looked at how can I factor everything and cancel any like factors, and then every limit does end up in direct substitution once you algebraically manipulate it from there. Let's look at example 14. So example 14, why don't you guys pause the video and read that statement out loud to yourself. So example 14 says the limit as x approaches 1 of x squared plus x minus 2 all over x minus 1. What do you guys think? Will direct substitution work in this case? So if I directly sub in, let's see what happens. I get 1 squared plus 1 minus 2 over 1 minus 1. Well, I'm already noticing that I'm going to get 0 in the denominator. Let's see what I get in the numerator. Well, in the numerator, I'll get 1 plus 1, which is 2. 2 minus 2 will give me 0 again. So again, I have this indeterminate form, so I'm going to have to go ahead and algebraically manipulate this limit so that I can be able to evaluate it. So direct substitution right away did not work. So what else do you think that we could try? So we can go ahead and factor this limit again. So I still have the limit as x approaches 1. Since I haven't taken the limit, I'm going back and starting from scratch since direct substitution did not work. And instead, I'm going to factor this. So in the numerator, x squared plus x minus 2 can factor as x plus 2 times x minus 1. Oops, let's extend that division bar, all over x minus 1, which we already have in the denominator. Now from here, I want to cancel any like factors, so the x minus 1s will cancel, and I end up with then just the x plus 2 that I have there when I canceled that out. What do you guys think? How have I done so far? Anything going wrong, or have I done everything correctly because I factored it and I canceled those factors? So I'm missing something, and it's really important that I have to have there. I have not taken the limit yet, which means I still need to have this limit as x approaches 1 in front of my simplified rational function now that I've canceled out those factors. So this x minus 1 here is extremely important. It's the entire part of the problem. This is a limit problem, and until I take a limit, I have to make sure I'm writing that down. Now that we've simplified this and canceled our factors, I'm going to go ahead and directly substitute in, and I'll end up getting 1 plus 2, and we get 3 then as our final answer on this limit. So in this case, factoring ended up being our way to algebraically manipulate again so that I could get that x minus 1 to cancel, which was the issue that was occurring in the denominator. And I just want to keep stressing the importance of this. I have to have this limit notation here and here, where I have those two arrows since I have not taken the limit yet. But as soon as I directly sub in, I have no more limit as x approaches 1 since I've done the direct substitution there. So as important as it is to write the limit when you need it, it's also important to know when you no longer write that limit. And one thing that you guys might be noticing through all of these is once you do the direct substitution and that those variables, which have been x for all of these examples, get substituted in for a numerical value, then the limit goes away. So pretty much if I have no more x's, I have no more limit then. It's a kind of a rule of thumb that you can think about. Now that's not always true depending on what your limit is that you're taking it of, but in all of these examples, once we subbed in directly, I can drop that limit expression in front. Let's look at example 15. Why don't you guys pause the video and try example 15 on your own first, and then we'll check it together. So example 15 says the limit as x approaches 2 of x minus 2 over x squared plus x minus 6. Now this one isn't as obvious right away if I'm going to end up with this 0 over 0 form. So let's see. If I substitute in directly, I'll get 2 minus 2 in the top. Well, that's okay. I can have 0 in the numerator. The denominator, I'll get 2 squared plus 2 minus 6. So I'll end up with 0 over, well, 4 plus 2 minus 6 is unfortunately going to leave me with 0 over 0. That is an indeterminate form, so I need to algebraically manipulate this somehow. So direct substitution right off the bat did not work. But of course, especially in a problem like this, if you don't recognize that you will end up with 0 in the denominator right away, it's definitely worth it to try it and see if it works. Since it did not, I'm going to have to go ahead and algebraically manipulate it. Since I have a quadratic, there's a good chance that I can probably factor it. X minus 2 is already factored in the numerator. And then in the denominator, x squared plus x minus 6 will factor as x plus 3 times x minus 2. Which conveniently, we can see this kind of ends up working out each time here. The x minus 2's are canceling, which is what's really giving me that issue of having a 0 in the denominator. Because the x plus 3, when I sub in 2 there, I get 5, and that's okay to have in the denominator. I have not directly substituted in yet, so I want to make sure I'm still writing the limit as x approaches 2 of 1 is what I'm left over with in the numerator over the x plus 3. Now I can go ahead and do a direct substitution, and subbing in 2 in place of that x will give me 1 over 2 plus 3, so I end up with 1/5. As my final answer for example 15. And in this case, our factoring was our key again to algebraically manipulate. Let's look at example 16. Why don't you guys pause the video and try example 16 on your own first. So example 16 says the limit as x approaches -3 of the square root of 9 minus x. Well, I don't have a fraction here anymore. The only thing I'd have to worry about here is the square root function has a specific domain. So as a little refresher, if I have the function f of x equals the square root of x, the domain of this function is x can be anything that is greater than or equal to 0 because we are only going to be working with real numbers here. And if I substitute a negative number into a square root, I get an imaginary number, which is still an answer, but in calculus, we're going to just focus on our real answers. So let's see if direct substitution works, because there's definitely nothing I can factor here since I have a square root. When I substitute that in, I'll get 9 minus a -3. Don't forget about that double negative there. So I end up with the square root of 12. Well, the square root of 12, it's not a perfect square, but it's still a valid numerical answer. It's an irrational number. If you want to reduce it down, it does reduce down to be 2 times the square root of 3, since you have that perfect factor of 4, that is a factor of 12. But actually, either of these answers would be correct on an AP test, especially if it's a free response. You do not need to simplify. Of course, if it's a multiple choice, we have to make the answer match. And so if the square root of 12 wasn't an option, but 2 times the square root of 3 is, then we would go ahead and reduce it down. So in this case, direct substitution did work. I still got a valid numerical answer out since I have a positive number inside of the square root. So since I did direct substitution right off the bat, I don't have that limit in front since I have replaced the x with a -3 already. Let's look at example 17. So in example 17, it says the limit as x approaches 0 of the square root of x plus 4 minus 2 all divided by x. Well, if I try to do a direct substitution, I can tell right away that I'm going to have an issue because I'm going to end up with a 0 in the denominator. And in fact, if I directly substitute in on top, I'm going to end up with the square root of 4, which will give me 2, and then 2 minus 2 is going to give me 0. So this is an issue. I ended up with an indeterminate form since I got 0 over 0. So far, all we've talked about is, well, how can I factor these? Well, when I have a square root, it's probably not going to be the easiest to factor these, so instead we have to come up with a different way to algebraically manipulate this still. And that way is going to be to use conjugates. As a little refresher back from an algebra or a maybe pre-calculus course, a conjugate, you might remember them more from imaginary numbers, but a conjugate, if I was talking about imaginary numbers, a plus bi and a minus bi would be what we call complex conjugates. We have the same thing if I have radicals. So if I had a plus the square root of b and a minus the square root of b, those would be what we call conjugates as well. In this case, our square root comes first, so what we're going to end up doing is flipping the sign in between to get our conjugate. So our conjugate here will be the square root of x plus 4, so that x plus 4 is not changing since it's all inside the square root, but what will change is the sign in front of the 2. That will become a plus 2 then. To manipulate with our conjugate, what we're going to do is we want to multiply by the conjugate. The reason being is that ends up getting rid of the square root. So if I look at this original problem, let me just rewrite it out so that I have enough space. So I have the square root of x plus 4, minus 2 all over x. What I want to do is I want to multiply by the conjugate. So I want to multiply by that square root of x plus 4 plus 2. And that way when I multiply and FOIL all of this out in the numerator, I'll end up with no more radicals. But it's not fair for me to just multiply the numerator by the conjugate because I'd be changing the problem. Instead, I have to also multiply the denominator by the conjugate, so that technically all I'm doing here is multiplying by the number 1. So what I've done here, I'm going to box it in red. This right here, that's really just equal to the number 1 because I have the exact same thing over itself. So if I had like 10 over 10, that would reduce down to be 1. Same thing here, if I have the square root of x plus 4 plus 2 all over the square root of x plus 4 plus 2, that's going to reduce down to be equal to 1. So I like to call this our fancy number 1 that we've got to figure out. And it's fair game to multiply by the number 1 since that's the identity and won't change the problem. All right, let me scroll down because we're going to need some space with this one. So from here, what I'm going to do is I'm going to FOIL out the entire numerator. So the limit is still going to be here since I have not actually taken the limit yet. And when I multiply out the entire numerator, I have the square root of x plus 4 times the square root of x plus 4. That will just leave me with, I'll write it out in painful detail this first time, the square root of x plus 4 squared. Then I'll get plus the square root of x plus 4 times 2. So I'm going to actually just put that 2 in front of the square root if I can fit it. Then I'll get minus then 2 times the square root of x plus 4. And then the last one, negative 2 times a positive 2 will give me negative 4 all over. In the denominator, I'm not going to FOIL it out, and we'll see why in a second. I'm just going to leave that alone as our original denominator of x times our conjugate. Now in the numerator, I have a positive 2 times the square root of x plus 4 minus 2 times the square root of x plus 4. So those guys are going to cancel each other out. That's the nice part about the conjugate, is that the middle terms cancel out when you end up FOILing them. And then for this first term, the square root of x plus 4 squared, well, the square root and the square cancel, and I just end up with an x plus 4. So in our numerator here, I still have my limit in front of this entire thing since I have not taken a limit yet. and I'll have the limit of x plus 4 minus 4 all over x times the square root plus 2. Just so that I have enough space, I'm going to go ahead and erase our little review over here that we have. The next thing I notice is that plus 4 and minus 4 cancel each other out, and I end up with the limit as x approaches 0. So I haven't taken the limit yet, so I have to make sure I'm still writing it, I get x in the numerator over x times our conjugate. Oops, that was a plus 4 plus the 2. Now from here, we can see why I didn't want to multiply out the denominator. So in the numerator, all I got left with was an x, and that is going to cancel very nicely with the x in the denominator. And this x in the denominator was our original issue that we had going on, since when I did a direct substitution, I got 0 then in the denominator. So now that those cancel, I can finally take a direct substitution on my limit, and we have the limit as x approaches 0. I have 1, since the x canceled out, over my conjugate, plus 2. And again, I still have that limit since I haven't actually taken it. Now that I can evaluate this directly, I'll get 1 over the square root of 4, since I'm subbing in 0 for x, plus 2. Square root of 4 is 2. I end up with 1 plus 2 of 2 plus 2, so I end up with 1/4. I can barely fit, that whole thing in right there. There we go. So as we can see through example 17 here, when we have to deal with a conjugate, it does get a little bit more messy there with all the algebra, but there's still an algebraic way to manipulate these, and we can multiply by the conjugate in both the numerator and the denominator. As we multiply that all out, our issue will end up canceling out, and then we can end up doing a direct substitution. Let's look at example 17. Or example 18, I'm sorry. So example 18 says the limit as x approaches 9 of x minus 9 over the square root of x minus 3. What do you guys think? Will a direct substitution work for this problem right away? So in this case, a direct substitution is not going to work. I'm going to fit it up here on top and we'll see why. So if I do a direct substitution, I'll end up with 9 minus 9 in the numerator. Well, that's okay. The issue becomes is that I get the square root of 9 minus 3, which ends up giving me 0 over 0. Since the square root of 9 is 3, 3 minus 3 gives me 0. So I have this issue again. I have to go ahead and do something else, and I have to algebraically manipulate it. Now, I could attempt to factor this out. There is a way to do it using factoring. It's not personally my preference. I would prefer to use the conjugate here since I have that square root. I just think it's a little bit easier to see. So what is our conjugate going to be for this problem? What do you guys think that conjugate will be? So our conjugate has to deal with the radical term. So our square root is in the denominator this time, and that's okay. So we're starting off with the square root of x minus 3, which means our conjugate will be the square root of x plus 3. Why don't you guys go ahead and finish off this problem by multiplying by the conjugate to the top and the bottom of this fraction, and then we'll check it together at the end. So I'm just going to go ahead, rewrite that original problem so you guys can get started from there. Okay, let's check this together. So I'm going to multiply by the conjugate over the conjugate. So I'm technically multiplying by that fancy number 1, so I'm not changing the problem in any way. When I do this, I'm going to make sure I'm putting parentheses around everything since it's technically that quantity times the other quantity. Now, in this case, I want to only multiply out where I have the two conjugates. So I'm going to only multiply out the denominator, and I'm actually going to leave the numerator alone. So in the numerator, I still have this x minus 9 times our conjugate. In the denominator, square root of x times the square root of x will give me the square root of x squared, which will just be equal to x. Then I'll get the square root of x times 3, so plus 3 times root x. Then I'll get negative 3 times root x. And then lastly, I'll get negative 3 times 3, so I'll get negative 9. Again, I still have that limit in front of this since I haven't actually evaluated the limit yet. From here we get to play this cancel game. So the 3 times the square root and the negative 3 times the square root will cancel each other out. Oops. We end up with the limit still as x approaches 9 of this x minus 9 in the top over, times our conjugate, all over x minus 9. Well, look how convenient that is. That x minus 9 ends up canceling out from there, and we end up with the limit still. So I haven't taken the limit, so I still need to write it, of just the square root of x plus 3. Technically all over 1, if you want to write that fraction still, but we don't need to. Now from here I can do a direct substitution, and I end up with the square root of 9 plus 3, so I get 3 plus 3, which will give us 6. That will be our final answer for example 18. So in both example 17 and 18, we ended up getting this indeterminate form when we did a direct substitution of 0 over 0. So because of that, there has to be some way to algebraically manipulate it. Since I had the square roots, I was going to lean towards using a conjugate, although you could attempt to factor these and see where that gets you as well. And then by multiplying, when I do the conjugate, I just have to make sure that I'm technically only allowed to multiply by the number 1. So it's very key that when you multiply by the conjugate, you also divide by that conjugate. And so this piece that I'm multiplying that I'm going to box in red here, remember this is just equal to that number 1, so I'm not changing the problem in any way, since multiplying by 1 leaves the problem unchanged. Okay, let's look at example 19. So in that original list that we had, I had direct substitution as the first way we want to try. We had factoring, we had conjugates, and then I also had a common denominator in there. Chances are this might be where the common denominator is going to come into play, but let's see if I can do direct substitution. So why don't you guys pause the video and see what happens when you directly substitute in. So when I directly substitute in, I've got fractions within fractions here. So this problem says the limit as x approaches 0 of 1 over x plus 2 minus 1/2, all divided by x. So when I do a direct substitution, I am getting a 0 in the denominator because of that x down there. So chances are direct substitution is not going to end up working out. And in the numerator, I get technically a 1/2 minus a 1/2, so I get 0 over 0 then. Oops, that got very messy. So in this case, just like before, I have to figure out some way to algebraically manipulate this because this is going to be an issue since I have our indeterminate form of 0 over 0. So in this case, I'm not going to attempt to factor. I don't have a conjugate that I'm going to worry about since there's no square roots. Instead, I want to get a common denominator. And where I'm going to focus getting a common denominator is actually in just the numerator portion of this problem. And the reason being is I've got fractions within fractions. This is a complex fraction, and I want to go ahead and reduce this down as much as I can and then worry about taking the limit. Because really right now, what I'm taking the limit of is extremely messy, and I just want to kind of remanipulate that portion of it. To get a common denominator here, I'd have to focus on what my least common denominator would be. So when I'm looking at 1 over x plus 2 minus 1/2, what is our least common denominator? So our LCD here would be 2 times x plus 2. Since I have an x plus 2 from the first guy and a 2 from the second guy, and they have no other factors in common, so 2 times x plus 2. I'm going to want quite a bit of space for this problem as well. When I take this then, I'm going to multiply the 1 over x plus 2 by the part of the LCD that is missing. And then I'm going to do the same thing to the 1/2 and multiply by the part that is missing. So out of my LCD on this first term, I'm missing that 2. So I'm going to multiply this first fraction by 2, but again, I've got to multiply it by 2 over 2, so I'm not changing the problem. Likewise, I'm going to multiply the second guy by the part of the LCD that is missing, which is the x plus 2. And again, I've got to multiply it to both the top and the bottom, so I'm technically only multiplying by the number 1 here. When I do that then, I still have, of course, this limit, and I still have my original denominator of x. This first guy is going to give me 2 over 2 times x plus 2 minus x plus 2 all over 2 times x plus 2. Now, yes, I know I could cancel stuff out here, but that's not my goal. My goal is to get it down to be one fraction, And now that I have a common denominator, I can go ahead and rewrite this numerator so that I have all of this over my LCD, since I have 2 times x plus 2 and a 2 times x plus 2. And in the numerator of my top part of my fraction, I'll get 2 minus, don't forget about these parentheses here, since that negative sign is technically subtracting off the entire x plus 2 quantity. Now that I have that, what I can go ahead and do is I technically have fraction over fraction, and I can multiply by the reciprocal of the denominator here. So I'm going to go ahead, I still have my limit, because I haven't done any calculus yet. I'm doing just a lot of algebra right now. In the numerator up here, I'm going to leave it untouched, even though we can simplify it, and I will in the next step. But we get this 2 minus x plus 2 over 2 times x plus 2 times the reciprocal of x is going to be 1 over x then. I'm going to continue to simplify this down a little bit so I get the limit as x approaches 0. Now in the numerator, when I distribute this negative sign, I have a 2 minus a negative 2, so those guys will cancel each other out, and I just get left with a negative x on top over 2 times x plus 2 times that x that we had from multiplying by the reciprocal. This looks a lot nicer than the original problem that we started with inside this limit up here. This is extremely messy up here that I'm boxing. This looks a lot better, and actually I can reduce it even further. I have a common factor of an x over x that can get canceled, and I end up with the limit as x approaches 0 of a negative 1. Since the x canceled, I still do have that invisible 1 there, over 2 times x plus 2. This looks a lot nicer, and if I do a direct substitution now, it will work out. So if I directly substitute in that 0, I'll end up with negative 1 over 2 times 2, so I end up with negative 1/4 then for my answer for this limit. So again, the conjugate and the common denominator is a lot of algebraic manipulation that we're working through and a lot of skills we're bringing back from prior classes. But once we've reduced those and simplified them down, the limit themselves is actually really nice to take because a direct substitution will work. And it's valid to do all this because I haven't changed the problem. I'm just manipulating how it's written by using things like multiplying by a fancy number 1 to get a common denominator as I simplify it down. Okay, the last type of example we're going to talk about in this video has to do with what happens when you deal with some absolute values. So I do have a review on the side that we'll talk about in a second, but let's look at this first example. So question 20 says the limit as x approaches negative 4 from the left of the absolute value of x plus 4 over x plus 4. Notice, that in all the examples we've done so far in this video, they were the two-sided limit, the limit from both the left and the right. In example 20 here, it looks like they just want us to deal with the limit from the left, and then if you're looking down at 21 already, we're just going to deal with the limit from the right. But in both of these, what we're taking the limit of is equal. The issue here is these absolute value bars. So if there weren't absolute value bars, then I could just cancel the x plus 4s and say that I'm taking the limit of 1. But I can't just ignore the absolute value bars. I have to think about what's happening there. And that's where our review over here comes into play. So what I'm reviewing for us is the definition of an absolute value. So the absolute value of a function is actually defined to be piecewise, meaning that there's two parts to the definition. And depending on what the value is that you're substituting in for x, will tell us which part of the definition I'm using. So the absolute value of x is going to just be the original x if that value that you're substituting in is greater than or equal to 0. So if I substitute in a positive number or if I substitute in 0, we know that the absolute value doesn't change anything and I just get that number back out. So that corresponds to our first kind of y example here. The absolute value of 2, we know is just going to be equal to 2 since 2 is already a positive number. In the second case, if the number that I'm substituting in here is negative, so if that x value is negative instead, I actually end up with negative times the original number. And that seems a little funky because you might be thinking, well, the absolute value should always produce a positive number. But remember, this number itself here, that x, is a negative number. So if I take a negative number and I multiply by a negative sign, I get a positive number overall. So let's look at it through taking the absolute value of -2. So here, the number that I'm taking the absolute value of is negative. So using this definition, I end up with negative times the original number, which is -2. Well, negative times a negative gives me a positive, and we knew that the absolute value of -2 should end up being +2. Algebraically, though, the reason that happens is because I'm actually taking the original number inside the absolute values, so that whole -2 here, and multiplying by a negative, which is why I have this extra negative for the second part of this piecewise definition. The reason we're going to use this is we're going to determine if the absolute value of x plus 4 is in the top portion or the bottom portion of this definition, and from there we can figure out then if I just get to drop the absolute values or if I have to multiply by a negative sign. And this is something that comes up kind of throughout this year that we're going to see in calculus in different contexts. And it's not a calculus concept, it's actually going back to an algebra concept, and we want to kind of have this definition in the back of our mind as we're going through these. So let's look at this limit. So we're taking the limit as x approaches -4 from the left-hand side. So as I am approaching from the left-hand side, I have to think about what types of numbers, what direction that's coming from. So if I'm on a graph, I'm going to want the negative values. So if I'm on a graph and I'm at -4, and I'm approaching from the left-hand side, think about some numbers that you're passing through to get to -4. Well, some of those numbers that I think about that we're passing through is like -4.1, -4.01, -4.001, as I keep getting closer and closer to -4. So think about this as a direct substitution. If you were to directly substitute in -4 itself, I'd end up with 0/0. Because I'd get -4 plus 4 on both the top and the bottom, which is why a direct substitution here is not going to work because of that case. So we have to think about some way to manipulate it, and we're algebraically manipulating it by using this definition over here about what an absolute value is. Well, as I approach from the left-hand side, because that's key here, as I approach from the left-hand side, this x plus 4, which is inside the absolute value, so this x plus 4 is the one I'm specifically looking at, this value is actually going to be less than 0 as I approach -4 from the left-hand side, because numbers that I'm subbing in would be like -4.1, and if I do -4.1 plus 4, I'm going to get a negative value. Because of that, I'm using the bottom portion of this definition that the absolute value of x plus 4 is really equal to negative times the x plus 4. I still do have my limit since I haven't actually taken a limit yet. I'm instead just thinking about which part of the definition here I'm using for the absolute value. And because the stuff inside the absolute value, that x plus 4 is going to be negative as I approach from the left-hand side, then because of that, I end up with this bottom part of this definition, and the absolute value of x plus 4 is equal to negative times the x plus 4. That's a big concept, and I want you guys to let that absorb and soak in. I think it'd be a great idea to pause the video and kind of read through that explanation on your own to make sure that we're fully understanding that. Now that we've taken care of the absolute value and kind of algebraically manipulated it to use the definition, I can cancel the x plus 4s, and I end up with the limit as x approaches -4 from the left of just -1. And we know from our summer assignment, if I'm taking the limit of a constant, that's just going to be equal to the constant itself, since it doesn't matter what I'm technically approaching, since there is no variable in there. So all of this comes down to looking at what side of the limit I'm approaching. Since I'm approaching from the left, then as I substitute in numbers for x, like -4.1 for instance, when I substitute that in, I get -4.1 plus 1. That produces a negative number, so that means the stuff inside the absolute value is negative, So by definition, if the stuff inside the absolute value is negative, the way the absolute values go away is by multiplying by a negative sign. So that's how I got this negative sign right here that I'm going to make very bold, times that original x plus 4. Now we can do the same thing with example 21. So example 21, the only portion that changes here is the side that we're approaching from. In this case, I'm approaching negative 4 from the right-hand side. So as I approach from the right-hand side, I want to think about values I'm subbing in. Well, in this case, I would be subbing in like negative 3.9. So the x plus 4 here that's inside this absolute value, in this case, is going to be greater than or equal to 0, since as I approach in from the right-hand side, those values that as you sub them in closer and closer and closer as you're taking the limit, those values are producing numbers that are still positive. What that tells me then is I'm looking at the top part of the definition, which says that the absolute value of a positive number is just the number itself. So this is the nice case where I can actually just drop the absolute value signs. So the absolute value of x plus 4 is just x plus 4 over, well, the original denominator that we had there. Again, because I haven't taken a limit yet, I'm still writing that limit in front. But the reason this comes down to is I'm looking at the stuff that is inside this absolute value. I'm going to go ahead and highlight it instead. So I'm just looking at this x plus 4, and since this x plus 4 is greater than or equal to 0, I'm dealing with the top portion of the definition of an absolute value, which means that the absolute value bars really don't do anything since the number itself is already positive. So I can just go ahead and drop those absolute values, and I get left with just x plus 4. Just like we did before, now that the absolute values are taken care of, I can go ahead and cancel those out, and I end up with the limit as x approaches, let's fix that, as x approaches negative 4 from the right-hand side of technically just 1. Again, I'm taking the limit of a constant, that's just going to give me the constant itself, which will be equal to 1. So as we can see here, in example 20, even though examples 20 and 21 are both looking at the limit of the exact same thing, it really depends on what side you're approaching for an absolute value. And when I'm approaching from the left-hand side, in this case I ended up with a negative 1. When I approached from the right-hand side, I ended up with the positive 1. So if you've looked down in your notes, you can see that it's coming, but our last example here is, well, what's the overall limit then? What happens if I take the limit as x approaches negative 4 of this absolute value of x plus 4 over x plus 4? Well, what do you guys think happens with the overall limit if the left-hand limit was equal to negative 1 and the right-hand limit was equal to positive 1? Well, if the left-hand limit is negative 1 and the right-hand limit is positive 1, those two numbers are not equal, so this limit then does not exist. Remember, DNE is does not exist, and the reasoning is because the limit from the left doesn't equal the limit from the right. But let's talk about how we're going to properly justify that. So if I'm properly justifying the limit from the left doesn't equal the limit from the right, then I have to rewrite out the entire problem again. So the limit from the left was this first statement here. That does not equal the limit as x approaches negative 4 from the right-hand side of our function here. And our function that we were dealing with this time was the absolute value of x plus 4 over x plus 4. So if I'm going to justify it out, this is using proper notation right here. If I just say left doesn't equal right, that is not proper notation. And if this is a free response or open-ended question, you would not be getting full credit if it asked you to justify why. So when we're justifying why limits don't exist, we have to make sure that we're using all the proper notation of the limit as x approaches whatever number. So in this case, negative 4 from the left of the function. Make sure you're writing the function in here. Does not equal the limit as x approaches negative 4 from the right. That is a plus sign of our function again. So I got to have all the pieces. The left limit, the right limit, and the functions that have to be inputted. Okay. So in this video, we went through quite a few algebraic examples of, well, the direct sub, the nice examples that we started with. If that doesn't work and I do a direct sub and I get 0 over 0, which is what we call an indeterminate form, I need some way to algebraically manipulate it. we used factoring, we used conjugates, and we used common denominators. We then also looked at this special case of what happens when I have an absolute value with an indeterminate form, and how can I think through this from both the left and the right side of our limit and really go back to the limit definition of a limit can only exist if the limit from the left equals the limit from the right.